Hello everyone, we are going to make some educational videos on physics. The intended target audience for our videos are class 11-12 students preparing for competitive exams like JEE Mains, JEE Advanced and NEET, and also other such competitive exams like BITSAT, etc. First year university students who have taken physics courses like mechanics, electromagnetics, etc. These videos are also for students preparing for physics Olympiads. So the content will be uploaded every week. So you will find at least one video every week, maybe sometimes maybe sometimes more. Please let us know how you find these videos and if you want anything to change in this or not. Today's topic, we are going to just give a general brief introduction to the field of physics. Then we are going to talk a little bit about what are units and physical quantities. Then the main thing that we are going to discuss in today's video is dimensional analysis. And then we are going to use the principles of dimensional analysis to solve some problems. And we can get to know how dimensional analysis can be applied uh, to solving some practical problems that we might encounter. So let's get started. So physics is one of the fundamental natural sciences studying the laws of inanimate nature. The universe consists of material bodies which are in permanent interaction and motion. The study and explanation of the laws governing the connections between various processes and phenomena are the fundamental aim of every branch of science. The analysis of interaction of material bodies and the laws of electromagnetic phenomena is the aim of physics. The general course of physics is subdivided into five subdivisions, namely mechanics, molecular physics, electromagnetics, optics, and atomic and nuclear physics. The laws of material motion are studied in mechanics. The other parts of physics cannot be studied without mechanics since various displacements and velocities are observed almost in all physical phenomena. So mechanics is generally believed to be the starting point from which one generally takes a deeper look into physics, that is into physics at a university level or even a pre-university level, that is for class 11th and 12th. Mechanics is usually subdivided into three parts: kinematics, statics, and dynamics. In kinematics, the motion of the bodies is considered irrelative to the factors causing the motion or changing its characteristics. That is, we are not concerned about is causing the what is causing a particular body to move in a particular fashion. We are just concerned with the particular motion that a body is carrying out and how that motion is going to change at any given time in the future. So we are not concerned with what is causing that particular motion. We are just concerned with how that motion will continue um, going forward. Statics deals with laws of equilibrium of the bodies. That is, when things are not moving uh, and things are static, that is, things are not moving, and the body is still in a state where it is kind of like where it is maintaining its state of like being not in motion. It's completely not doing anything. Then what are the laws that are governing such a type of phenomena? Dynamics studies the laws of motion and the causes producing the motion and changing it. Taking these three together, kinematics, statics, and dynamics, we can get a very good idea about mechanics of material bodies and rigid bodies. I think an interesting thing is that in most of the studies, what we do is that we study first the kinematics, that is how how a body moves when when it has a particular velocity, particular acceleration, and it is moving in a particular direction, and then how in a future instance will the body move, or where will the body be. That is usually covered in kinematics, and then we learn the Newton's laws of motions and other dynamical principles, which kind of help us to understand how this motion is being caused. What are the causes behind this motion? Okay, so in daily life, if you have a cricket ball in your hand and you throw it in a particular way, then the trajectory of the cricket ball, or the way the cricket ball moves, that is the kinematics of the cricket ball. While what is causing the motion of the cricket ball, that is you're throwing it and you're applying a particular force on it, and there is a particular air resistance acting on it, causing the ball to swing a bit, causing the ball to swing in the air to some extent. So that is all that comes under dynamics. And statics is a special, can be considered a special a case of dynamics where there is no motion occurring, but the dynamical laws that we will discuss in dynamics can then be applied in such a way that there is no motion. Then what is the resulting situation? An example of this static could be like, uh, you have a particular you have a bench, and on that there are like, lots of different loads being placed on the bench, and then you want to find out like, okay, what how much is like, how these loads are, like how the bench is able to bear these loads, and you would like to find out like, if suppose you place if suppose you transfer this load in a particular manner, will this still remain stable and will this still not move, or will this kind of like, this bench topple over. Things like that can be dealt with the understanding of statics. Now let us talk about physical quantities and units. I wouldn't go into much detail here because this is generally a very basic thing that you can read up in any book, and it's very fundamental, and uh, it's basically physics is an exact science where there are measurements, where there are calculations and mathematics involved. And whenever there are any measurements, suppose you have a piece of a wooden stick given to you, then how would you convey the information about this wooden stick to someone else? Of course, you will take the wooden sticks, you will measure it, and you will note you will take a note of its how much is its length, and then you might also take a measuring scale and weigh how much the wooden sticks how much is the mass of the wooden stick. And you might also go a step ahead, and instead of just measuring the length, you might also measure the width of the stick, that is how thick the wooden stick is, things like that. So these kind of things have to be conveyed when you are talking about physics with other people. So these kind of things involve things like, things like units and physical quantities. Now in this case of the wooden stick, the length of the wooden stick and the width of the wooden sticks, these are physical quantities which have a particular unit, which have a particular unit. So you can measure the length of the wooden stick and its width in suppose you are using the SI unit, you will measure it in meters. Or if you are using if you want to use imperial units, then you can give the length and the width in the units of inches or feet, something like that. The same goes for other physical quantities. So generally there are seven fundamental physical quantities that have established measurement standards. And so for the quantity like time, which is a very fundamental quantity, the unit of the unit of time is second, and it and then you have length. The unit of length is generally a meter, For mass, it's generally measured in kilograms. Amount of a substance is something that you might come across in chemistry or later on in atomic and nuclear physics. So that is generally given in terms of moles. And later on, when you study thermodynamics, you might encounter thermodynamic temperature, or you can, for just sake of convenience, you can just think about it as a temperature. It's given in the units of kelvins, and electric current has the unit of amperes, and luminous intensity is measured in candelas. Now let's talk about the main topic that we would be discussing here. That is dimensional analysis. So as we have seen, every measured or calculated quantity has an associated dimension with it. The units in which the quantities are expressed do not affect the dimension of the quantities. An area is still an area whether it is expressed in square meters or square feet or acres for that matter. Like we were discussing the earlier example of you have a wooden stick and you are trying to measure its length. So you can use to measure its length, you can use a scale which uses inches as its base unit, or you can use a scale which uses meter or centimeter as its base unit, or you can use a scale which uses feet as its base unit. But it is important to understand that what is being measured here is the dimension of length, the length of the wooden stick. And the same goes for its mass. You can measure its mass in kilograms, in grams, or you can measure it in pounds or ounces, things like that. So all these are different ways to measure the same dimension, or to calculate, to quantify the same dimension. So the units that are used to measure does not affect the dimension of the physical quantity. For mechanical quantities, mass, length, and time are elementary and independent of each other, so they can serve as fundamental dimensions. Other quantities can then be expressed in terms of these fundamental dimensions. Let us look here at the let us look here at example of velocity. Velocity is generally understood to be as something about like how much distance or how much displacement you cover in some time. So it has the dimensions of length over time, and here we will be using square brackets to and here we will be using brackets to denote that we are trying to find the dimension of the entity given inside the square bracket. So here the dimension of velocity v is length over time, which is L over t, or L t to the power minus 1. Now let's look at acceleration. Acceleration is generally something as like change in velocity over time. So that has a dimension of length over time square. That is L over t to the power t square, or L t to the power minus 2. Force is generally considered like force. The formula for force is mass times acceleration. So the dimension for force has the dimension of mass multiplied with the dimension of acceleration. So the dimension of mass is m, and the dimension for acceleration, which is a derived dimension, which is a dimension derived from length and time, is L t to the power minus 2. So the dimension of force is m L t to the power minus 2. Another important thing to know about dimensional analysis is that any equation must be dimensionally consistent. That is, dimension on the right hand side and on the left hand side should both be the same. They cannot be different. That is, you cannot compare two different types of dimensions. The dimensions of the when you are writing an equation, what it means is that the left hand side is equal to the right hand side. That is, you are comparing the two entities one on the right hand side and one on the left hand side, and the things that you're comparing must always have the same dimensional. Additionally, if on the right hand side, suppose you have addition of multiple entities, like you have a plus b plus c, d equals to a plus b plus c, then in this case the dimension of d should be equal to the dimension of a, and the dimension of a should be equal to the dimension of b, and the dimension of b should be equal to the dimension of c. So basically, in an equation, all the different separate entities would have to have the same dimension for it to be dimensionally consistent. Let's look at an example. Generally, the displacement x under a constant acceleration a that a particle undergoes is generally given by x is equals to half a t square. So this is the equation that we are going to look at. Now let us look at the dimension of the quantity x, and the dimension of this quantity x should be equal to the dimension of this quantity a t square. This half is a dimensionless constant. It does not enter into our it's a dimensionless constant, so it does not matter. So now let us look at the right hand side of this equation, that is a t square. So this has a dimension of acceleration multiplied by square of the dimension of time. So dimension of acceleration we saw last in the previous slide, that it is L t to the power minus 2, and then the dimension of time square is t to the power 2. So basically we'll be left with a right hand side will have the dimension of length. And now let's look at the left hand side, that is we'll look at this dimension of x. Dimension of x, since it's calculating a displacement, it is length L. So we have that the dimension of left hand side is equal to the right hand side. So this equation is dimensionally consistent. So this equation is valid. So later on you might as you progress forward in your physics education, you might have to remember different formulas and things like that, and you might sometimes derive some formula or derive some sort of a relationship on your own. And so at that time you can use dimensional analysis as a kind of like a sanity check to see if whether, okay, so you know that a displacement under a constant acceleration of a particle starting from rest is half at square, but suppose you are not exactly sure whether it is half at square or half at or half at cube. So in that case you can just quickly uh, uh, use dimensional analysis to see that, okay, the only thing that gives a dimensionally consistent equation is half at square. So that way you can use dimensional analysis to aid in your problem solving going forward. Now we'll be looking at some illustrations, and let's start with our first problem that we'll be discussing. So you have you have a string, and on that there is some sort of a mass attached, and it is being set into a circular motion, that it's going around and around. So you can think of it as some kind of a flywheel or something of that sort, or just you have a string and you have a small mass attached to it, and you are kind of moving it around over your head in a circular direction. So in that case, the string will have a centripetal force F that is being generated inside it because of the motion. So this centripetal force F, apart from any dimensionless constant, must depend on the mass m of the object that is attached at the end of a string, the velocity v of the object as it's going around in a circular path, and the radius of the circular path. So let's start with this thing. Centripetal force F is it's proportional to some mass raised to the constant a, raised to the indice a, some velocity raised to the indice b, and some radius raised to the indice c. So this is the proportionality relationship that we are trying to find, and our aim here is to find out what are these a, b, c, so that we can get a rough idea of how this force would vary if we are changing the mass, or we are changing the velocity, or we are changing the radius of the circular path. So the dimension of F must be the same as the dimension of this product m raised to a, v raised to b, and r raised to c. So the dimension of force is m l t to the power minus 2 on the left hand side, and then on the right hand side we have m raised to a, L by T raised to B, and L raised to C. On simplifying, we get that ml t to the power minus 2 is equal to m raised to A, L raised to B plus C, and T raised to minus B. Then we will compare these two sides, and we can find out the values for this constants a, b, and c. So when we compare the exponent of m, that is the exponent of mass, on left hand side and on right hand side, then on left hand side we have m raised to 1, and on the right hand side we have m raised to a. So we get that a is equal to 1. Then let's compare the exponent for t, that is time. The exponent for time on left hand side is minus 2, and the exponent for time on right hand side is minus b. So we get that b is equals to 2. Then let's compare the exponent for L. The exponent of L on left hand side is 1, while that on the right hand side is b plus c. So we get b plus c equals to 1. From previous comparison of exponent of t, we get that b is 2. So finally we get the answer that c is minus 1. So finally we arrive at the result that the centripetal force F is proportional to m v square by r. So this gives us a fair idea of how this centripetal force F will vary if suppose we say we double the mass of the that is attached to the string, and then we also double its velocity. So if we double the mass and double its velocity, then the force will increase by 8 times. It will increase by twice because we are doubling the mass, and then it will increase by 4 times because we are doubling its velocity. So the final increase would be 8 times. Similarly, if we are just increasing the mass by 2 times, and we are also increasing the radius by 2 times. So in this expression we can see that if we are replacing m by 2m and r by 2r, those two will cancel out and the centripetal force would remain unchanged. So this dimensional analysis can give us such dimensional analysis can give us a result within the limits of a dimensionless constant. So we won't be able to know what this dimensional constant exactly is, but we'll get a relationship where you can roughly get an idea that if you're making certain changes in the physical quantities, then what would be the resulting change in the quantity that we are interested in. Now let's look at the second example. Now this is a very pedantic kind of example where we are trying to find the dimensions of Newton's gravitational constant G. So F equals to G m1 m2 by r square is something that you will learn later on in mechanics if you're not already familiar with this. This is Newton's laws of gravitation. So here in this case, this force, this F is a force which is the gravitational force due to two objects of mass m1 and m2 that are placed at a distance r apart, and this G is the Newton's gravitational constant. This is not a dimensionless constant. This constant has dimensions. So now we are going to use dimensional analysis to find out what are the dimensions of the Newton's gravitational constant G. So let's start. So we have this equation F equals to G m1 m2 by r square. Let us see how are the dimensions of this equation. So we'll have to, the dimension of F will be equal to the dimension of G multiplied by dimension of m1 multiplied by dimension of m2 divided by dimension of r square. So we have ml t to the power minus 2 equals to the dimension of G multiplied by m1 multiplied by m square and divided by L square. So we have ml t to the power minus 2 equals to the dimension of G multiplied by m raised to the second power and L raised to minus 2. So we can simplify this equation and we can take this m raised to 2 and L raised to minus 2 on the other side, and then it goes into the denominator, and finally we have that the dimension of G is ml t to the power minus 2 divided by m raised to 2 and l raised to minus 2. So once you do the math, you get that the dimension of G is m raised to minus 1, l raised to 3 and t raised to minus 2. So these are the dimensions of Newton's gravitational constant. Let's look at another example. So what we are trying to find here is that we are going to use dimensional analysis to find the period of oscillations of an oscillator. So now what we are given is that the time period of an oscillator depends on its mass m, a restoring force constant k, which has the dimensions of m, l to the power minus 2 and t to the power minus 2, and the amplitude a with which the oscillations are which the oscillations are basically undergoing. So this amplitude a has the dimension of length. Now let's look at this thing. So let's start and let's call that, like, time period of oscillations be, let time period of oscillations be t, amplitude be a, mass be m, and force constant be k. So we know that the dimensions of the force constant are m, l to the power minus 2, t to the power minus 2, and then we know that this expression would, this time period of oscillation would be proportional to the amplitude a raised to the exponent a, and the mass m raised to the exponent b, and the force constant k raised to the exponent c. So then we check the dimensions of these quantities that are involved here. So we have the dimension of t will be equal to the dimension of the amplitude raised to a, the mass raised to b, into mass raised to b, into the force constant raised to c. So we have, so the time, so this is basically so this t, time period of oscillation, will have the dimension of time as it's given in its name itself. So it will be m raised to 0, l raised to 0 and t raised to 1 on the left hand side. Then on the right hand side we have this a raised to a. So a is, this has the amplitude, amplitude is basically length. So this is length raised to a, this is l raised to a. This mass m has the dimension of mass, that is m. This will be capital M mass raised to b. And the force constant, it has a dimension of m, l to the power minus 2 and t to the power minus 2, that is raised to the exponent c. So finally, when we collect all these terms on one side, we'll have this m raised to b plus c. Here b is coming from this m raised to b, and the other c is coming from the dimension of force constant. And l, we'll have a, l raised to a, this is because of the amplitude, and then we have this minus 2c that is coming from the force constant. And finally we have this time period, dimension of time raised to the minus 2c because of the force constant. When we compare the exponents, let's compare the exponent of t. The exponent of t on the left hand side is 1, and the exponent of t on the right hand side is minus 2c. So we have minus 2c equals to 1, which gives us that the value of c is half, minus half. Then let's compare the exponent of m. The exponent of m on the left hand side is 0, and on the right hand side it is b plus c. So we have b plus c equals to 0, which means that b equals to minus c. So b equals to minus c will give us that this b is equal to minus of minus half, that is plus half. The exponent of l, when we compare the exponent of l on the left hand side and the right hand side, we get that on the left hand side we have 0, and on the right hand side we have a minus 2c. So we get that a minus 2c is equals to 0, which gives that a is equals to 2c. So we get that a is minus 1. Now let's look at how this pans out. So yeah, so we have here the time period t is directly proportional to the amplitude raised to minus 1, mass m raised to half, and the force constant k raised to minus half. Here, yeah, force constant k raised to minus half. So on simplification, we see that this t is proportional to amplitude a raised to minus 1 multiplied by under root m over k. This t is proportional to 1 over the amplitude multiplied by under root m over k. So this gives us a fair idea of how the time period of oscillation of the oscillator depends on these three physical quantities. So suppose if we are reducing the amplitude by half, then we know that the time period will go up by will double. On the contrary, if we are increasing the amplitude by twice, then we know that the time period will fall by half. And similarly, different changes in mass. Suppose we are um, increasing the mass by 4 times, we know that the time period will increase by twice. So in such way, we can get a general idea of how the time period of the oscillator will vary depending on the different physical parameters. Now let us just explore how things would look if we choose a different set of physical quantities as fundamental dimensions. Remember that in the remember that the standard case for mechanical phenomena is that we choose mass, length, and time as the fundamental dimensions, and then uh, we find the other dimensions in terms of these fundamental dimensions of mass, length, and time. But let us just, for sake of curiosity, let us choose mass, time, and velocity as different set of fundamental dimensions which are independent of each other. Using these, let us find the dimensions of displacement, acceleration, and force. The choice of fundamental dimension affects how the dimensions of the derived quantities turn out, as you will see in the coming slide. Yeah. So we are just like looking at an alternate scenario where we have chosen mass, velocity, and time as the three independent fundamental dimensions, and depending on these three, we will find out the dimensions of the other quantities. So displacement is basically velocity into time. So the dimension of displacement d would be v times t. Now let's look at acceleration. Acceleration is basically change in velocity uh, per unit time or something, change in velocity over time. So acceleration, the dimension of acceleration would be the dimension of velocity divided by the dimension of time. So that will be v over t, which you can also write it as v multiplied v times v into t times t to the power minus 1. So we know that force is mass times acceleration. So in this alternate uh, in this alternate scheme of things where we are choosing mass, velocity, and time as the fundamental quantities, let us look at what will be the dimensions of force. So the dimension of force would be the dimension of mass times the dimension of acceleration, which will be m multiplied by v t to the power minus 1. So the dimension of force uh, in this alternate case where we are considering mass, velocity, and time as the fundamental quantities, fundamental dimensions, we get that the dimension of force in this is m to the m raised to 1, v raised to 1, and t raised to minus 1. This is slightly different from what we get from considering mass, length, and time as the fundamental quantities. But one thing is for sure is that these, whether you're considering the fundamental quantities as mass, length, and time, or mass, velocity, and time, what you're getting is that you're not getting the same result as such, but you are describing the same physical quantity in terms of the fundamental dimensions that you have chosen. That is these are physically consistent. These are not giving you any wrong results. But since you have changed the fundamental dimensions, you're getting different results. So this is important to know that sometimes you might experience you might encounter a problem where it will be said that instead of choosing mass, length, and time as the fundamental dimensions, choose mass, velocity, and time, or maybe something else, mass, acceleration, and time. So using the changed definition of fundamental quantities, then you might be asked a question. Okay, then tell what is the dimension of force, or tell what is the dimension of work, tell what is the dimension of power, something like that. So let's just summarize what we have learned today. We know that dimensional analysis can be a useful tool to find a relation for an unknown quantity, like we have studied for the time period of an oscillation, within a factor of the dimensionless constant. So you can use the tools of dimensional analysis to get a rough idea of, what an unknown quantity would be and how it would change depending upon the other parameters in the consideration. Then it can also be used to check whether a given equation is correct or not. Like I said, later on when you would be learning physics for some time, you will have to remember different relations and different equations and stuff like that. So suppose if in the moment that you are trying to solve a problem and you're not exactly sure whether the displacement of an object moving under constant acceleration with zero initial velocity is half at square or half at cube or half at. So in that case, you can just use the tools of dimensional analysis to quickly check which is the correct answer, and for this case it is half at square. So the I hope you have understood what we are trying to uh, study here. That is, I hope you have understood what dimensional analysis is and how it can be used for different things, and how it can help you in solving some types of problems. You will encounter this dimensional analysis, or you will be getting back to this topic every time you are kind of like exploring a new topic. You would always suppose when you are learning work and energy and these type of concepts, you'll always kind of like discuss what is the dimension of work, what is the dimension of energy, and you will check whether the equation that you have arrived for work is dimensionally consistent or not. The next video that I'll be uploading would be on kinematics. Uh, it it's bound to be in multiple parts, so you can check that out. And please let me know if you have any feedback and what do you think about this. And also let me know if you want more problem solving in during the videos. And uh, yeah, let me know if you want more problems to be solved during the videos. And if you have some questions or if you have some problems that you would like me to solve for you, you can put it in the comments and let me know. Please do like, share, and subscribe to the channel. And let me know in the comments what feedback you have.